Okay, let's unpack this. Have you ever watched like a high-speed car race, Formula One maybe,
Oh, yeah.
and you hear the announcers talk about cars tearing around the circuit?
That track they're on.
Exactly. That defined track they keep lapping, right?
Yeah.
Returning to where they started. It's all about completing that journey.
Yeah, the lap.
Well, today we're taking that familiar idea and applying it to something just as fundamental, but, often a bit more mysterious: electricity.
Right.
We're diving deep into what an electric circuit actually is, that essential defined path electricity travels to do, well, pretty much anything.
And for you listening in, our goal here is to really demystify it completely.
Yeah.
We want to give you a really clear, sort of beginner-friendly understanding of what an electrical circuit is, how it works at its most basic level,
Right.
and why this basic concept is just so crucial to almost everything around us.
Mm-hmm.
Our mission really is for you to gain clear knowledge without feeling like totally swamped by jargon.
Definitely want to avoid that.
Think of it as your shortcut, maybe, to understanding the electrical world.
Absolutely. And we've pulled together some fantastic materials for this, stuff specifically designed for absolute beginners.
That's the key. Starting simple.
So if you've ever felt a little in the dark about how electricity actually moves, you're in the perfect place. We're going to, well, shine a light on it together.
Good plan.
So let's start right back with that car racing analogy, that track.
Okay.
Imagine that perfectly designed racetrack. It's a closed loop, isn't it?
It has to be.
Cars start at a specific point, they zoom around, and eventually they complete a single lap. Brings them right back to their starting position.
Back where they began.
It's a defined path, always leading back to the beginning.
And what's really remarkable here is how perfectly that analogy works for electricity.
Right.
An electrical circuit is essentially the same idea. It's a defined path where electricity, specifically electrons, travels in a complete loop.
So electrons are like the tiny race cars.
Kind of, yeah. Just like the race car leaving and returning, electrons start a journey from a power source.
Okay.
They move through a path, and then they return to that same power source. They don't just, wander off. They absolutely must complete their full lap.
Okay, that makes sense. So if they have to complete a loop, what happens if that loop gets broken somehow? Does the electricity just stop?
Precisely. Yeah, that's exactly it. And this brings us to a really critical concept. Electricity will only flow if that circuit is complete, or what we call closed.
Closed, okay.
Think about it like a physical chain. If any link in that chain is broken,
Right.
the chain itself can't do its job, can it?
Nope. Falls apart.
Same way with electricity. If any part of an electrical circuit is broken or like a light switch being off, the electrons just cannot complete their journey.
Okay. The path is blocked.
Exactly. They can't make it all the way back around, so nothing happens. If your light switch is off, the circuit is open, the lamp stays off.
Simple as that.
No electricity flows, no work gets done. It's kind of an all-or-nothing game.
That makes perfect sense. So it sounds like the design is just as crucial as the components themselves then.
Absolutely.
Electrical circuits aren't just random connections. They are specifically built, arranged
Purposeful.
to perform a particular job, whether that's lighting a bulb or, I don't know, charging your phone.
Exactly. Every circuit has a purpose.
Now, if these circuits can get incredibly complex, I mean, inside a computer or something,
Oh, yeah. Millions of connections.
how do engineers even begin to make sense of them all?
Uh-huh.
Is there a kind of shorthand they use, like a map?
That's a great question. And it leads us to something, well, truly ingenious, I think. The power of symbols.
Symbols. Okay.
Engineers and technicians use visual symbols to simplify these complex circuits. These things called circuit diagrams or sometimes wiring diagrams.
Right.
They're like a map, just as you said. They allow anyone who understands the symbols to easily grasp how all the different bits and pieces are connected and what the circuit is designed to do without needing to see the actual physical wiring, which could be, a total mess.
That sounds incredibly useful.
Oh, it is. And a key point to grasp here is the global utility of these symbols. They create a universal language. An engineer in, say, Japan can draw a circuit diagram using these standard symbols.
Okay.
And an engineer in Brazil, speaking a totally different language, different culture,
Yeah.
can immediately understand that electrical design. It's a powerful testament to the clarity and efficiency of using visuals for complex information.
That's actually fascinating. A true international language of electricity.
Pretty much, yeah.
Okay, now that we've talked about these universal symbols, let's actually use them. Let's picture a circuit in action, maybe the simplest one we can imagine, like a light bulb with a switch.
Perfect example.
How do we start building that mental picture? What are the pieces?
Right. Let's walk through this simple circuit. We can imagine starting from the power source and sort of moving clockwise around the loop, just like the electrons would conceptually flow.
Okay, clockwise from the power. What's first?
First, you need something to get those electrons moving in the first place, right?
The push.
Exactly, the push. And that's the power source. In our simple example, that's maybe a battery or could be several batteries connected together.
Like in a flashlight.
Yep. Its crucial function is to create the voltage. You can think of voltage as the electrical pressure or the push for the electrons.
Okay, pressure.
And also provide the current, which is the flow or the amount of electrons actually moving. It's what drives the whole thing.
Got it. And the symbol.
Ah, right. On a circuit diagram for a direct current or DC source like a battery, it's usually shown as two parallel lines. One line is longer, representing the positive plus terminal. One is shorter for the negative terminal. And if you have multiple batteries hooked up in series to get more voltage, more push, you can just repeat that symbol. Long, short, long, short.
Simple enough.
Right.
Okay, so the battery gives the push.
Mm-hmm.
Where do the electrons go from there on their way to the light bulb?
Well, often we need to control that flow a bit. We don't always want the maximum current rushing through, and that's where the resistor comes in.
A resistor. Sounds like it resists something.
It does. Its function is basically to hinder electricity, as some books say. It reduces the current flow.
Right.
Think of it like a tiny bottleneck in a pipe, or maybe stepping on a hose slightly. It just makes it harder for the electrons to get through, controlling how many can pass.
Okay, so it manages the flow.
Exactly. And here's a kind of surprising insight. While resistance often controls flow and prevents damage, it's also the secret ingredient in things like toasters or electric heaters.
Really? How?
They deliberately use materials with high resistance to convert that electrical energy into heat. So they turn that hindrance into a really useful function.
Never thought of it that way.
Yeah. So every circuit has some resistance, even just in the wires themselves, but a dedicated resistor component is put there to precisely control the flow to a specific level.
Okay, controlled flow. Makes sense. What's next in our clockwise journey?
After the resistor, in our example, we encounter the lamp, or, what we usually call a light bulb in everyday language.
The thing we want to turn on.
That's the one. This is the component that actually performs the work in our circuit, the main job here.
Yeah.
Its function is to convert the movement of electrons, that electrical energy, into light energy.
Right, so this is where the circuit's action becomes visible.
Exactly. You see the result.
So we have the power, something to control the flow, and the thing doing the work. The lamp? What about turning it on and off? That feels pretty important.
Absolutely crucial. That's where the switch comes in. This is your basic on and off component.
Okay.
Its function is pretty straightforward. It either connects the circuit path or it breaks it.
Connects or breaks.
Right. So when you turn a switch on, you are physically connecting the circuit parts. And the term we use is closing the circuit.
Closing it makes it work. That sounds backward.
I know, it trips people up. Think of it like closing a drawbridge. When the bridge is closed, cars can cross. When the circuit is closed, electrons can cross.
Okay. Closing the drawbridge, completing the path. Got it.
Exactly. And when you turn the switch off, you are breaking the circuit path. We call this opening the circuit.
Like opening the drawbridge.
Precisely. Opening the drawbridge stops the traffic. Opening the switch stops the electron flow.
Okay, that analogy helps a lot.
Good. So in our light bulb example, if the switch is physically moved to the closed position, the circuit path is connected, electrons can flow all the way around.
And the bulb lights up?
And the bulb lights up. It's a perfect, simple demonstration of electricity needing that complete loop to do anything. I remember as a kid, I just thought switches, magically made things happen.
Yeah, me too.
But it's so much more logical knowing it's just literally breaking and making a physical path, isn't it?
It really is. Just connecting and disconnecting.
Finally, linking all these diverse components together, the battery, the resistor, the lamp, the switch, are the wires.
Can't forget the wires.
Definitely not. Their function is simple but absolutely essential. They provide the physical pathways for the electrons to travel on. They link everything together to form that continuous loop.
And on the diagram?
On a circuit diagram, wires are typically just represented by solid lines connecting the symbols for the other components.
Okay. So, putting it all together then. When that switch is closed, all these components, the battery providing the push, the resistor managing the flow, the lamp converting energy into light, and the wires connecting everything, they all form one complete unbroken loop.
That's the key. Unbroken.
And the electrons are then free to move. They complete their journey from the battery through everything and back again.
Back to the start.
And in doing so, they do work by lighting up that bulb. It's actually, well, it's remarkable how all these distinct components come together just right to achieve one specific function.
It really is quite elegant when you break it down.
So as we start to wrap up this deep dive, maybe take a moment, you listening, to reflect on how a seemingly complex idea, like an electrical circuit, can actually be understood through really simple analogies, like our racetrack, and just by breaking it down into its core parts.
The fundamental takeaway, really, is that electrons, the carriers of electricity, always need a complete and unbroken path to do their work. No path, no action.
Simple, but powerful.
And consider this. Every single smart device you own or interact with.
Like this phone I'm looking at.
Exactly. Your phone, your watch, even a self-driving car.
Yeah.
They're all built upon billions, literally billions, of these simple open-closed circuits acting in incredibly complex patterns.
Wow.
The basic principles we talked about today, the need for a loop, a power source, control, something to do the work, they're truly like the DNA of the digital world.
That's a great way to put it.
And maybe this raises an important question for you to think about. How many unseen circuits are buzzing away around you right now?
Probably countless.
Right. All following these fundamental principles. From the simple flashlight maybe tucked in your kitchen drawer to the super intricate systems inside your smartphone or, the device you're listening to this deep dive on right now. Electrical circuits are just ubiquitous. They're everywhere. Understanding these basics is truly the first step to understanding how almost everything in our modern world functions.
It really opens things up.
Yeah. And while sure there are many, many more symbols and way more complexities in the vast world of electronics, just grasping these core concepts, power, path, resistance, switching it, provides an incredibly solid foundation. It even hints at powerful principles like Ohm's law, which sort of governs how voltage, current, and resistance all balance out. But that's maybe for another day.
Definitely sounds like it.
Yeah.
But for now, understanding this basic loop is huge.
It's the starting point for everything else. You've got the foundation now.